Somewhere far beyond the light of any familiar star, two dark shapes are moving around one another. They do not announce themselves with fire. They do not shine with the heat of a star or scatter light from a solid surface. If the region around them is almost empty, an ordinary telescope might find no bright spectacle at all. It would see distant stars, deep darkness, perhaps nothing that looks like a collision waiting to happen. And yet the darkness is not still. Around each black hole, space is curved so deeply that light passing nearby would no longer keep a simple path. A star behind them might appear bent, repeated, or stretched into a thin arc around the edge of darkness. Time itself would not behave near their horizons as it does far away. The two black holes would circle a shared center slowly, at first locked into a gravitational dance that may have been forming for millions or even billions of years. A collision sounds sudden to the human mind. Two things meet, strike, break, and scatter. But black holes do not collide like stones or planets. They are regions of space-time boundaries, beyond which light cannot return, moving through a universe that bends around them. Their final union is not a crash between surfaces. It is a transformation of geometry. The strange beauty of this event is that it can be among the most powerful events in the universe while remaining almost invisible. It may leave no flash for ordinary telescopes. It makes no sound through the vacuum of space. Its message travels outward as gravitational waves ripples in space-time that can cross cosmic distances long after the two black holes have become one. Tonight we will follow that hidden event slowly. We will begin with two shadows in deep space, learn what their darkness means, trace how they become a pair, watch their orbit tighten, and picture what no telescope can simply film. Then we will follow the ripple outward across the universe until it reaches Earth and is recognized by instruments built to notice the faintest motion of space-time. How can two invisible black holes become one? And how did human beings learn to detect an event that no ordinary eye could ever see? Imagine a region of space so distant that the stars seem almost scattered by accident. There is no nearby sun filling the scene with warmth. No planet turns slowly in reflected light. No bright nebula gives color to the darkness. There is only a deep field of distant points, each one, perhaps a star, perhaps a galaxy lying far behind the place where the event is unfolding. At first, the scene appears empty. Then the background begins to bend. A star that should sit in one place seems to shift slightly. Another becomes stretched near the edge of something unseen. A small patch of distant light appears doubled, as if the universe behind the darkness were being folded around an invisible weight. The center of the scene remains black, but the space around it refuses to behave as empty space should. This is how the two black holes first enter the story. They are not visible as stars are visible. They do not glow with their own light. They do not offer the eye a surface, a color, or a shining outline. Their presence is known through disturbance light bent around them, orbits shaped by them, and most importantly, for this journey, ripples in space-time sent outward by their motion. The two shadows circle one another. The word shadows is useful only for a moment. A shadow is usually the absence of light caused by an object blocking it. A black hole is stranger. It is a region where space-time has curved so deeply that light crossing a certain boundary can no longer escape. The darkness is not painted onto the object. It is created by the paths that light is no longer able to take. From far away, though, the mind still needs an image. So we begin with two shadows. They move around a shared center, not because they are attached, not because anything is pushing them in a visible way, but because gravity has bound their motion together. Each is falling around the other. Each is continually missing the other. The path is not a straight plunge. It is a curve, then another curve, then another, drawn over and over in the dark. If the two black holes are still far apart, the movement may be patient. Their orbit can be wide. The change from one cycle to the next may be almost impossible to notice. In deep time, however, almost impossible is not the same as impossible. Something is leaving the system with every orbit. The dance is being slowly rewritten. That something is energy carried away by gravitational waves. We will return to those waves later, because they are the reason the orbit slowly tightens. For now, it is enough to feel the scene: two black holes circling in a darkness that is no longer empty. The silence around them is not inactivity. It is the silence of motion, too deep for human senses to receive directly. A black hole collision is often described in a way that makes it sound like a sudden impact. The phrase is understandable. It gives the mind a simple event to hold two things meet and become one. But the real story is more gradual and much stranger. Long before the final merger, the two black holes are already linked by gravity shaping each other's future with every orbit. They do not collide like boulders. There are no surfaces waiting to break, no crusts, no molten interiors exposed, no shards of black hole flying away. The event is a change in space-time itself. Two boundaries of no return move through a shared gravitational field until the geometry no longer allows them to remain separate. At the end, there is one black hole where there were two. The path toward that ending may be ancient. Before these black holes became a pair, they may have been massive stars. They may have burned with fierce brightness, lived quickly, and collapsed into dark remnants after violent deaths. Or they may have met later in a dense cluster where old stellar remains gathered under gravity and exchanged partners through close encounters. The exact history can be difficult to recover, but the final pair carries traces of its past in its mass's spins and orbital motion. By the time we see them here, their separate histories have become one shared event. The universe around them continues on its own vast scale. Stars form elsewhere. Galaxies turn slowly. Light crosses the dark for ages. Planets orbit distant suns. Nothing in the scene has to hurry. Gravity is patient enough to work through time spans that make human history feel like a flicker. The black holes keep circling. Every orbit is almost like the one before it, but not quite. Their separation becomes a little smaller. Their rhythm becomes a little faster. The gravitational waves they emit become slightly stronger. The final merger is still ahead, but it is already being prepared. This is the slow cosmic event at the heart of the documentary. It is not a fireball racing through space. It is not an explosion that fills the sky with visible light. It is a tightening relationship between two regions of extreme gravity. The event is powerful because space-time itself is involved. It is quiet because the main messenger is not sound or ordinary light. It is visual only when we learn how to read what the darkness changes. The first direct gravitational wave detection, later named GW150914, gave humanity a concrete example of this hidden drama. The signal reached Earth on September 14th, 2015. In the data, scientists found the pattern of two black holes spiraling together, merging and settling into one final black hole. The event had happened far away and long before the signal reached us, but the gravitational wave still carried its shape. It was not a photograph. It was not a telescope image of two dark circles becoming one. It was a tiny change in distance inside an instrument on Earth, a faint stretching and squeezing caused by a wave that had crossed the universe. From that signal, scientists reconstructed the event, the final orbits, the merger, and the ring-down of the newly formed black hole. This changed the meaning of observation. For centuries, astronomy depended mostly on light, and its relatives, visible light radio waves, infrared, ultraviolet X-rays, gamma rays. Each new form of light opened a new sky. But a black hole merger offered something different. It showed that the universe could be studied through the motion of space-time itself. The event in deep space did not need to shine in order to be known. This is why the opening image is so important. Two shadows in deep space are not beyond understanding. Their darkness is difficult, but it is not absolute silence to science. They bend light, they shape orbits, they produce gravitational waves as they move. They leave evidence in the universe around them. The eye alone would struggle. The mind, guided by physics, can go farther. There is another reason the opening scene should remain slow. If we rush too quickly toward the final collision, the black holes become only an event. But in deep space before the merger, they are also a relationship. Their motion is not a single act. It is a long conversation between gravity and time, between distance and loss, between two horizons that can never shine, yet can still shape everything around them. From far away, the system might seem almost peaceful. The black holes follow their orbit, and the background universe remains wide and quiet. There may be no visible sign that the pattern is changing. A distant observer, without gravitational wave instruments, might see only darkness, or perhaps the faint distortion of starlight around something unseen. But the calm is not permanent. The orbit contains its ending from the beginning. Once gravitational waves begin carrying energy away, the pair is no longer simply repeating itself. It is changing in a way that may be too slow to notice at first, but too deep to stop. Every orbit leaves a trace that will never return to the pair. Every ripple sent outward makes the old separation slightly less possible. This is what gives the scene its hidden tension. Two black holes can seem like the most final objects in the universe, the collapsed remains of stars sealed behind horizons, cut off from ordinary light. Yet even they are not frozen. Even they can move pair spiral merge and become something new. A black hole may hide its interior, but it cannot hide its gravity from the universe around it. That gravity is the first visible clue. It bends light. It pulls matter into orbit. It shapes the path of another black hole. It writes patterns into space-time. The event begins not with a flash, but with the slow discovery that darkness can have behavior. This is why a black hole merger is such a powerful subject for calm narration. It asks us to replace sudden spectacle with patient attention. The closer we look, the less the darkness feels like an empty background. It becomes a place of hidden motion, where the largest changes may arrive without color, sound, or warning. The two shadows continue to circle. They do not know they are being watched. They do not know that billions of years later, perhaps a planet will build instruments sensitive enough to measure the faintest trace of their motion. They do not send a message with intention. Still, their orbit becomes a message because the universe allows motion to leave marks. The story then is not only about two black holes. It is about how reality can be active beneath the threshold of sight. Imagine the background stars again. As the black holes circle, the star field behind them would appear restless. Light skimming near their horizons might be deflected into arcs or repeated images. A star hidden behind one black hole might appear beside it, its light curved around the dark boundary. If both black holes are close together, the distortions overlap and change as they orbit. Even without direct light from the black holes, the scene has motion. The darkness has structure. If gas is nearby, the picture can become brighter. Gas pulled toward the black holes may heat and glow before it crosses an event horizon. It may form streams, disks, or turbulent flows, depending on the environment. Such matter could give telescopes something to see. But many stellar mass black hole mergers may occur in places with little surrounding gas. In those cases, the central event remains dark to ordinary sight. That does not make it less real. It makes the story more subtle. We are learning to follow an event whose most faithful signature is not brightness, but motion. The black holes are not seen by what they emit from inside. They are known by what their gravity does outside. Their orbit becomes a kind of language. The shrinking of that orbit writes itself into gravitational waves. Those waves travel outward, keeping the rhythm of the final dance long after the dance has ended. At the source, the merger is immense. At Earth, the signal is tiny. That contrast will return throughout the documentary because it is one of the deepest wonders of the subject. A cosmic event can release enormous energy in gravitational waves, yet arrive at our planet as a disturbance so faint that only extraordinary instruments can recognize it. The universe can be vast and delicate at the same time. Before we follow the signal to Earth, we need to remain near the event itself. We need to understand the two shadows one at a time before the orbit becomes too complex. A black hole is not simply a dark object. It is a boundary in space-time. It has mass. It may spin. It curves light and alters time near its horizon. Its darkness is not emptiness, but a limit. That limit is where the next section begins. The two shadows are circling, but to understand their dance, we must first approach the edge around each one, the place where light disappears and where ordinary intuition begins to give way to curved space-time. Before we follow two black holes deeper into their shared orbit, we need to pause beside one of them, not close enough to fall, not close enough for the idea of escape to become uncertain, only close enough in imagination to see why a black hole is not an ordinary object. It does not have a surface like a planet. It does not have a glowing edge like a star. It does not offer a boundary the hand could touch or a wall the eye could see. What it has is an event horizon. The event horizon is the boundary beyond which light cannot return. Outside it, escape is still possible if the path and energy are right. Inside it all, future paths lead deeper inward. The horizon is therefore not a material shell. It is a limit written into the geometry of space-time. If a traveler crossed it, there would not necessarily be a sudden impact at the boundary itself. There is no physical membrane waiting there. Yet after crossing, the meaning of outward and inward would have changed. The universe outside would still exist, but returning to it would no longer be part of any possible future path. That is the source of the blackness. A black hole is dark because light that crosses its horizon cannot come back to an observer outside. It is not merely a body that absorbs light efficiently. It is a region where the structure of space-time prevents escape. The darkness is gravity made absolute at a boundary. To understand that boundary, we need Einstein's idea of gravity. In daily life, gravity feels like a pull. A stone drops, a river flows downhill, feet stay on the ground. The earth seems to tug things downward, and for ordinary experience, that description is natural. It works well enough for falling objects and familiar motion. General relativity reveals a deeper picture. Mass and energy shape space-time. Objects move through that shaped geometry. The sun does not simply pull Earth through empty space with an invisible thread. The sun curves space-time around it, and Earth follows a path within that curvature. Gravity becomes not only a force, but a description of how space-time is arranged. A black hole is what happens when that curvature becomes extreme. The mass is compressed into such a small region that the escape boundary forms around it. Beyond that horizon, even light, the fastest messenger in the universe, cannot reach the outside. It is not that light becomes weak or slow in its own local motion. It is that the geometry gives it no outward future. One gentle way to picture this is a river flowing toward a waterfall. Far upstream, a swimmer can move in many directions. Closer to the waterfall, the current becomes stronger. There may still be a chance to swim away. But once the water flows inward, faster than any swimmer can move outward, every path through the river leads toward the fall. The event horizon is similar in spirit. It marks the place where the inward flow of space-time in this analogy leaves no escape, even for light. The image is imperfect, but it carries the feeling. Near a black hole, our ordinary map of directions begins to fail. We imagine left and right, forward and backward, up and down. We imagine that turning around is always possible. But inside the event horizon, the center is not merely a place one could choose to avoid. It becomes part of the future, as unavoidable as tomorrow. This is why the black hole is so hard to visualize honestly. Human imagination wants surfaces. It wants shapes. It wants something solid to stand for the idea. But a black hole asks us to think in terms of boundary path, curvature, and time. It is not a dark planet. It is not a hole drilled into space. It is a region where space-time has taken on an extreme form. Even so, the space outside the horizon can speak clearly. A black hole can bend light from objects behind it. This gravitational lensing gives the eye or the instrument a way to notice the invisible. A star behind the black hole might not appear where it truly is. Its light may be deflected, stretched, or duplicated. Under certain alignments, light can form arcs or rings around the dark center. The black hole itself remains dark, but the surrounding universe becomes distorted. The distortion can become especially strange near what physicists call the photon sphere. This is a region outside the event horizon where light can, under ideal conditions, orbit the black hole. The idea feels almost impossible at first. Light is supposed to travel forward, crossing space at the fastest possible speed. But near a black hole, the curvature is so strong that the path of light can be bent into a circle. Such orbits are unstable, meaning a tiny change can send the light outward or inward, but the idea itself reveals how deeply the black hole reshapes motion. For the imagination, this matters because it gives the black hole a ghostly visual richness. Light from the background universe can travel along strange paths before reaching an observer. Some light may pass close once, some may loop partway around, some may be delayed, bent, or multiplied. The image around a black hole is not a simple silhouette. It is a complicated arrangement of what light was forced to do before escaping toward the eye. This is why black hole images can show bright rings, distorted disks, and strange duplicated structures. The ring is not the event horizon itself glowing. It is the behavior of light and matter outside the horizon, shaped by gravity. The event horizon remains the deeper boundary, the place beyond which light no longer returns. Around it, however, there can be a region of extraordinary visual complexity, almost like the universe is folding its own image around an unseen center. Now add a second black hole. The visual field becomes even more difficult. Light may bend around one horizon, then pass through a region influenced by the other. The background may be distorted in a changing moving pattern. In a close binary, the lensing effects do not sit still like a single black hole against a fixed star field. They rotate, overlap, and shift with the orbit. This is where the merger begins to escape simple drawing. A classroom diagram can show two circles and a spiral. It can show arrows, paths, and waves. But the actual space-time around two close black holes is far more dynamic. The paths of light, the shape of the horizons, and the outgoing gravitational waves all belong to one evolving geometry. That evolving geometry is what makes black hole mergers so different from familiar collisions. When two ordinary bodies collide, the surfaces matter. With black holes, the horizons matter, but not as hard surfaces. The event is governed by how space-time itself changes. The boundary of no return becomes part of a larger moving structure. This also changes the emotional meaning of the event horizon. It is tempting to imagine the horizon as a kind of cosmic prison door, a line where everything ends. But in the merger story, the horizon is not only an ending, it is also a participant in motion. Two horizons can orbit. They can distort. They can approach. They can finally be replaced by a single larger horizon. The boundary is dark, but it is not inert. A black hole is therefore not just a final point in a star's life. It can become part of a new event. That idea is deeply important. A massive star collapses, and one might think the story is finished. The star no longer shines. Its interior is sealed. Yet in a binary system, or dense stellar environment, the black hole can still enter another chapter. It can meet another black hole. It can orbit. It can lose energy. It can merge. It can help produce a gravitational wave signal that crosses the universe. In this sense, black holes are both endings and beginnings. They end the visible life of certain stars. They begin new gravitational histories that may remain hidden for immense stretches of time. The event horizon marks a limit for light, but it does not mark a limit for consequence. This is why we must be careful with the word darkness. Darkness in this story does not mean simple blankness. It means that one kind of information cannot escape. Other kinds of information remain available outside the horizon. The black hole's mass affects orbits. Its spin can influence nearby spacetime. Its motion in a binary system generates gravitational waves. The interior is hidden, but the exterior is full of clues. The merger is built from those clues. When two black holes circle, each one carries an event horizon, and each one curves the space around it. Their shared orbit is a pattern outside both horizons. The gravitational waves come from the changing shape of that outer spacetime. The signal that reaches Earth is not a message from inside the black holes. It is a message from their motion around each other before and during the final union. This distinction gives the whole documentary a clearer foundation. The event horizon hides the interior. The orbit reveals the relationship. If hot gas surrounds the black hole, a second kind of visibility appears. Gas falling inward can heat to extreme temperatures, glowing before it crosses the event horizon. Around some black holes, this matter forms an accretion disk, a bright and turbulent structure that can make the neighborhood of the black hole shine powerfully. But the glow belongs to the matter outside. The horizon itself remains a boundary of no return. This distinction will matter when we return to merging black holes. Images of glowing disks and fiery swirls can help us imagine black holes in certain environments. But many black hole mergers detected through gravitational waves may not produce a visible flare. The main event can unfold in a region where little matter is available to shine. The horizon hides the interior, but the exterior still leaves evidence. Matter may orbit. Stars may move around an unseen mass. Light may bend. Time may be affected. Gravitational waves may be released when black holes move together. Science works outside the boundary, reading the effects that remain available. A black hole, therefore, becomes both hidden and measurable. That combination gives it much of its power. It is not completely beyond knowledge, yet it marks a limit to what can be known from the outside. Information from inside the horizon cannot simply return. The deepest region is sealed from ordinary communication. But the black hole's mass, spin, motion, and influence can still shape the universe around it. This is where the single black hole begins to prepare us for the pair. If one black hole curves space-time, two black holes in orbit create a changing curvature. The geometry is no longer steady. The horizons move around each other. Their gravitational fields overlap and shift. the paths available to light and matter change from moment to moment. The system becomes dynamic, not only dark. Before we return to the pair, we should also understand where many black holes come from. A common path begins with a massive star. For most of its life, a star balances gravity against pressure produced by nuclear fusion. Gravity presses inward. Energy from the core pushes outward. The star shines because it is holding itself up against collapse. Massive stars live quickly. They burn through their fuel far faster than smaller stars. As fusion changes the core, the balance becomes harder to maintain. Eventually, for the most massive stars, the inner support fails. The core collapses. The outer layers may explode outward in a supernova. If the remaining core is massive enough, collapse continues until a black hole forms. Brightness becomes darkness. A star that once illuminated space leaves behind a boundary light cannot cross. The transformation is severe, but it is not disconnected from the rest of cosmic history. The material blown outward by massive stars can enrich space with heavier elements. Later stars and planets may form from that enriched material. Black holes are part of the life cycle of galaxies, even when they themselves no longer shine. Stellar mass black holes like those involved in the first directly detected merger are only one family. Supermassive black holes sit in galactic centers with masses millions or billions of times the sun's. Their origins are still studied and debated. But for our journey, the stellar mass black hole gives the clearest path into the slow dance. A massive star dies, a remnant remains, and sometimes that remnant has a partner. The event horizon depends on mass. A more massive black hole has a larger horizon. A smaller one has a smaller horizon. From far away, a black hole's gravitational pull depends mainly on its mass, just as with other objects. It does not magically reach out and pull everything into itself. If something orbits far enough away with the right speed, it can remain in orbit. The extreme behavior belongs to the region near the horizon. This helps remove a common misunderstanding. A black hole is not a cosmic drain swallowing the universe indiscriminately. It is extreme because its mass is concentrated inside a very small radius. Far-away gravity follows the mass. Close in the compactness changes everything. This double nature is essential. A black hole can behave like an orbiting mass when viewed from a distance, and like an edge of space-time when approached closely. It can be part of a binary system, circling another black hole, while also carrying a horizon that no light can escape from. It is both a participant in orbital motion and a limit to visibility. When two such objects orbit the familiar and the strange overlap, we can speak of masses, orbits, and energy. Those ideas are familiar from celestial mechanics. But as the pair tightens the horizons and the space-time around them becomes central, the language of planets and moons can guide us only so far. Eventually, the system enters a regime where strong gravity takes over the story. That is why the event horizon is more than a definition. It shapes the entire merger. It tells us why we cannot expect light from inside the black holes. It explains why the final union is not an impact between surfaces. It shows why gravitational waves become such powerful messengers. The horizons hide, but their motion reveals. The two shadows in deep space are therefore not empty shapes. Each is a boundary with mass and perhaps spin. Each bends light. Each alters time nearby. Each may carry the afterlife of a massive star. When they enter a shared orbit, their darkness becomes a moving geometry. We are learning to imagine black holes by watching what they change. That is the quiet invitation of this section. Instead of picturing a monster, picture a boundary. Instead of picturing a surface, picture a limit. Instead of picturing darkness as blankness, picture a region where paths, light, and time have been rearranged by gravity. Somewhere two such boundaries may be circling. Their edges do not glow. Their interiors cannot report back. But outside them, the universe still reacts. Light bends, orbits form, space-time carries waves. And if two black holes are bound together, their future begins to turn inward. The next question is how that pairing happens at all. A single black hole can be born from collapse. But a merger requires companionship in darkness. It requires two remnants to become linked by gravity, whether through the lives of massive stars born together or through later encounters in crowded stellar environments. The final collision begins far earlier than the final second. It begins with how black holes find each other. A black hole merger is the ending of a story that usually began long before the final spiral. It may begin in a cold cloud of gas before any black hole exists. The cloud collapses under gravity and fragments into stars. Some are modest and long-lived. Others are massive, brilliant, unstable in the long run, and destined to burn quickly through their fuel. If two of those massive stars are born together, their shared orbit may survive through transformations that would destroy a more fragile system. By the time two black holes circle in darkness, much of the drama is already behind them. They did not simply appear side by side. Nature had to make each one then keep or bring them close enough for gravity to bind their future. That process can happen in more than one way, and the uncertainty is part of the fascination. A gravitational wave signal gives us the final motion clearly, but it does not always give a complete biography. Still, several roads are possible. The first begins with the binary star system. Many stars are born with companions. Two massive stars can orbit a shared center from the beginning of their lives, bright and short-lived by cosmic standards. Their motion may already contain the distant outline of a future merger, though nothing about the early system looks dark yet. At this stage, the pair may be luminous. They burn hot. They drive powerful stellar winds. They may exchange material if one expands and fills the gravitational region around it. Their masses change. Their orbit changes. One star may evolve faster than the other. What looks like a simple pair from far away may in fact be a complicated exchange of gas, gravity, and time. Then the first star dies. Its core collapses. The outer layers may explode outward. A black hole may remain. The system is suddenly altered. Mass has been lost. The orbit may widen or become more eccentric. If the explosion is asymmetric, the new black hole may receive a kick that changes its path. The binary may survive, or it may be torn apart forever. For a future black hole merger, survival matters. If the companion star remains bound, the system enters a strange middle phase, one black hole circling one massive star. The star continues to evolve. It may swell. It may lose material. It may interact with the black hole. Eventually, it too reaches the end of its life. A second collapse occurs. If the system survives this second transformation, two black holes are left in orbit. Two stars have become two shadows. This path feels almost like a story of companionship through death. Brightness fades from one partner, then the other. What remains is an orbit without starlight, a bond carried forward after both luminous lives have ended. The merger, when it finally comes, may happen long after the original stars vanished from sight. But this is only one path. Another begins in a crowded place. In dense star clusters, many stars and stellar remnants move within a relatively compact region. Over long times, heavier objects can sink toward the center, through repeated gravitational interactions. Black holes, being massive remnants, may gather there. In such an environment, close encounters become more common than they are in the sparse field of ordinary space. A black hole can pass near another black hole. It can interact with a binary system. A three-body encounter can eject one object and leave two others bound. Partnerships can break and reform over long periods. The cluster becomes a slow gravitational sorting ground, where dark remnants meet, not because they were born together, but because their environment brings them into contact. In this second path, the black holes meet later. The contrast is useful. Some pairs may be siblings born from massive stars that shared a life. Others may be strangers assembled by chance and gravity in crowded regions. Both can end in the same final image, two black holes spiraling together. But the hidden past may be different. Scientists look for clues in the gravitational waves. The masses of the black holes matter, their spins matter, the orientation of those spins can matter. If two black holes came from stars that evolved together, their spins might show one kind of pattern. If they met in a dense cluster, their spin directions might be more randomly arranged. These are not simple fingerprints, and the interpretation can be difficult, but across many detections, patterns begin to emerge. Every merger is therefore both an ending and a clue. It tells us that two black holes became close enough to merge. It may also hint at where they came from, what kind of stars formed them, what kind of environment shaped them, and whether they were bound from birth or assembled later. The final signal is brief, but it can open questions about the hidden architecture of stellar life and death. This is why black hole mergers are not merely isolated cosmic accidents. They belong to a population. When the first gravitational wave detection was announced, the event seemed almost singular in public imagination. Two black holes had merged, and humanity had detected the wave. But later detections showed that the universe contains many such events. Each one adds to a growing map of dark compact objects. The catalog is not only a list of collisions, it is a way to study how black holes form and pair across cosmic time. The merger we imagine may have taken one of several roads. It may have begun with two massive stars circling in the same system. It may have formed in a dense cluster. It may have involved black holes that themselves formed through earlier mergers, especially in environments where repeated encounters are possible. Some systems may be straightforward. Others may be more exotic. The universe does not owe us a single origin story. That uncertainty is worth preserving. A sleep documentary does not need to solve every formation channel. It needs to show that the final slow dance is rooted in a deeper history. Two shadows in deep space are not isolated symbols. They are products of star formation, collapse cluster dynamics, and gravitational patience. Let us picture the binary star path again more slowly. A massive pair forms in a stellar nursery. Around them, gas glows and disperses. The stars are bright, but their lives will be short. One expands and changes first. Material may flow between the stars. Winds remove mass. The orbit shifts. Then the first collapse comes, leaving a black hole where a star once burned. For a time, the system is half bright, half dark. The companion still shines. The black hole does not. If the companion loses gas, some of it may fall toward the black hole and glow before crossing the horizon. The pair may be visible then, not because the black hole shines, but because the matter around it does. Eventually, the second star reaches its own end. Another collapse, another horizon. The light that once defined the pair is gone. The orbit remains. Now imagine the cluster path. The setting is older, denser, more crowded. Stars pass near each other. Remnants gather toward the center. Black holes, invisible unless they interact with matter, move through a gravitational sea of companions and strangers. Encounters exchange energy. A black hole may be kicked outward. Another may capture a partner. A binary may harden through repeated encounters, becoming tighter each time another object carries energy away. In this path, the environment itself plays a larger role. The pair is assembled by the slow choreography of many bodies, not only by the life cycle of two stars. The final merger carries the memory of a crowded place, even if that memory is difficult to read from a single wave. Both paths lead to the same essential condition. There is also a difficult middle stage in many binary star stories, a stage that can bring two future black holes much closer together. In some models, one star expands so greatly that it begins to surround its companion inside a shared envelope of gas. This is often called a common envelope phase. The details are complex and still studied, but the basic image is useful. Two dense cores moving inside a larger cloud of stellar material, losing orbital energy as they interact with that envelope. The envelope can act like a brake. As the cores move through it, their orbit can shrink dramatically. Some of the orbital energy may help eject the envelope into space. If the system survives, the two remaining cores can be left much closer than before. Later, after further evolution and collapse, the result may be a compact binary capable of merging within the age of the universe. This matters because distance is everything. Two black holes can be bound together and still never merge if they are too far apart. Gravitational waves will carry energy away, but if the orbit is wide enough, the process may take longer than the current age of the cosmos. To create the mergers, we detect nature often needs a way to make the pair close enough before gravitational waves can finish the work. The early history prepares the final spiral. This is one reason black hole formation is so deeply connected to uncertainty. We know that black hole mergers happen because we detect their gravitational waves. But the exact route that produces each pair may remain partly hidden. The signal tells us about the final system, but the earlier stellar history must often be reconstructed through models, populations, and comparison. The story is like hearing the last sentence of a book carried across the universe. The sentence may reveal the tone of what came before. It may hint at the characters, the setting, the conflict, but it does not give every chapter. Scientists have to infer the earlier pages by comparing many endings. This is why each new detection matters. One merger can be beautiful and important. Many mergers become a population. A population can reveal patterns that single events cannot. If certain masses appear often, that says something about massive stars and their collapse. If spin directions appear random, that may suggest dynamic formation in dense environments. If spins seem aligned, that may support isolated binary evolution in some cases. The universe slowly becomes statistical. This may sound less poetic than one dramatic merger, but it is where the deeper knowledge begins. Science often moves from wonder at one event to understanding across many events. The first signal opens the door. The next signals show whether that door leads to a rare chamber or a large hidden landscape. Black hole mergers have begun to reveal a landscape. Some detected black holes are heavier than many early expectations for stellar remnants. Some events raise questions about how massive stars lose material before collapse. Some may point to environments where black holes merge more than once, creating larger black holes that later pair again. Not every event fits neatly into a simple story of two stars born together and dying into a pair. That complexity is good for the documentary. It prevents the story from becoming too mechanical. The slow dance has multiple possible origins. Some pairs are old companions. Some are late encounters. Some may be second-generation mergers, where one or both black holes are themselves the result of earlier unions. The final spiral looks similar in broad outline, but the path into it may differ. The black holes do not carry name tags. They carry physical properties: mass, spin, distance, waveform shape. Those are the traces available to us. From them, scientists build probability, not fairy tale certainty. A good script should preserve that uncertainty without making the science feel vague. We can say these are the main pathways, these are the clues, and the field is still learning how often each pathway occurs. This gives the listener a gentle sense of ongoing discovery. The merger is not only an answer, it is also a question sent back into stellar history. What kind of stars made these black holes? Did they live together or meet later? Did they come from a quiet, isolated binary or a crowded cluster? How many unseen black holes must exist if we are detecting mergers across cosmic distance? Each signal widens the darkness. It suggests there are more black holes than the eye could ever count. Some drift alone. Some orbit stars. Some sit in galactic centers. Some become pairs. Some pairs are too wide to merge. Others draw close enough that gravitational waves begin to dominate their future. The pair we follow is one of those. Whatever its origin, it has crossed the necessary threshold. It is close enough, bound enough, and persistent enough for the next process to matter. The formation story has handed the system to gravitational radiation. From here, the orbit itself becomes the main actor. Two black holes must become bound in an orbit close enough that gravitational waves can eventually draw them together. If they are too far apart, the time to merger may exceed the age of the universe. If the system is disrupted, they may wander separately forever, if they remain bound and close enough. However, the slow loss of orbital energy begins to matter. This is where deep time enters. A binary black hole may orbit for ages before the final signal. The early gravitational waves can be too weak to detect from far away. The orbit changes gradually, almost invisibly. But gravity is patient. The loss accumulates. What seems stable on one timescale becomes temporary on another. A human lifetime is too short to feel this patience. A galaxy has more time. The final chirp detected on Earth may last less than a second for some stellar mass mergers, but behind that brief signal may lie millions or billions of years of preparation. The stars had to form. They had to die. The black holes had to remain or become paired. The orbit had to tighten. The wave had to cross space. Human beings had to appear, understand relativity, build detectors, and keep them listening at the right moment. The final signal is short because it is the end of a long sentence. This helps the merger feel less like an isolated spectacle and more like a cosmic biography. A black hole may seem abstract, a mathematical darkness, but many black holes have ancestry. They come from stars, from clusters, from galaxies, from histories of collapse and encounter. Their merger is part of the larger life of the universe. Brightness becomes remnant. Remnant becomes pair. Pair becomes spiral. Spiral becomes wave. Wave becomes knowledge. That sequence is one of the quiet spines of this documentary. It also reminds us that the word collision is too small. By the final moment, two black holes are merging. Yes. But what merges is not merely two isolated objects. Whole histories converge: stellar evolution, gravitational dynamics, strong field relativity, cosmic distance, and human detection. The two shadows have pasts. They may not carry visible scars. Their horizons do not display a biography. But their masses and spins can hold clues. A black hole that is unexpectedly massive may raise questions about the stars that formed it. A pair with unusual properties may suggest a special environment. A population of detections can reveal what single events cannot. This is one reason gravitational wave astronomy feels like listening to a hidden forest. One event is a sound in the dark. Many events begin to reveal the shape of the unseen landscape. Some signals are common, some are rare, some fit expectations. Others stretch them. With each detection, the population of black holes becomes less theoretical and more textured. Still before detection comes the orbit. Once two black holes have become a pair, their future depends on the separation between them and on how energy leaves the system. If the orbit is wide, the pair can circle for an immense time. If it is already tight, the final merger may arrive much sooner. In either case, the key question becomes unavoidable. Why does the orbit shrink? Nothing in the darkness appears to touch them. No gas may be present. No third object may be nearby. The two black holes circle as if the pattern could continue forever. But the pattern is slowly paying a price. Their motion disturbs space-time. That disturbance travels outward as gravitational waves. And with the waves goes energy that the orbit cannot keep. The pair has found each other. Now their dance begins to change. At first, a binary black hole system can look like a promise of repetition. One black hole circles, the other answers. Together they move around a shared center. Turn after turn in a darkness that may contain no glowing matter at all. If we imagine watching from a safe distance, the motion seems almost steady. A loop becomes another loop. The shape continues. But an orbit is not always a closed story. In this system, each turn leaves something behind. The black holes are losing orbital energy through gravitational waves. These waves spread outward through space-time, carrying away part of the motion that once kept the pair at its old separation. The loss may be small at first, almost beyond noticing. Over enough time, it changes everything. The orbit tightens. This is the central mechanism of the slow dance. The black holes are not pushed together by an outside hand. They are not pulled inward by a visible cable. Their own motion creates waves in space-time, and those waves carry energy away. As the system loses energy, the only orbit left to it is a closer one. The idea is simple in outline, but strange in feeling. On Earth, losing energy often suggests slowing down. A spinning wheel loses energy and gradually stops. A thrown ball loses energy and falls. But gravity can invert our expectations. When two bodies in orbit lose energy, the orbit can shrink, and in a smaller orbit, the bodies move faster. The pair appears more intense as it radiates energy away. The dance quickens because it is losing something. This quiet paradox gives the in-spiral its shape. At wide separation, the gravitational waves are weak. The orbit changes slowly. The black holes may complete countless cycles while the distance between them decreases by only a little. But as they come closer, their motion grows faster. Faster motion creates stronger waves. Stronger waves remove energy more quickly. The orbit shrinks faster still. A feedback begins. Closer means faster. Faster means stronger radiation. Stronger radiation means closer again. The process remains calm in our narration because it may unfold over immense time, but the physics is relentless. The system is sliding down a gravitational path, not in a straight line, but in a spiral. Each orbit is a little smaller than the last. Each wave carries away a little more of the old arrangement. A familiar analogy is a pair of dancers circling across a floor that slowly narrows beneath them. At first there is room. Their steps are wide. The pattern repeats comfortably. Then the circle tightens. They turn more quickly. The movement becomes more focused, less spacious, more difficult to separate into leisurely stages. The end is not a stumble. It is the natural completion of the narrowing pattern. For black holes, the floor is space-time. The narrowing is caused by gravitational radiation. General relativity predicts that accelerating masses can create ripples in space-time. Most objects produce waves far too weak to matter. Earth and the Sun emit gravitational waves, but the effect on Earth's orbit is negligible for human concerns. Ordinary systems do not radiate gravitational waves powerfully enough to change their motion in any dramatic way. Binary black holes are different because they are compact, massive, and capable of orbiting extremely close together. Compactness matters. A pair of ordinary stars would touch or exchange material before reaching the same kind of close gravitational regime. Black holes can approach until only a few horizon lengths separate them. There is no solid surface that stops the orbit earlier. Strong gravity dominates. Velocities become enormous. Space-time changes rapidly around them. That is when gravitational waves become powerful. The waves do not glow as they leave. They do not sweep dust aside like a blast of wind. They pass outward as changes in geometry, stretching and squeezing space as they travel. Near the source, they carry tremendous energy. Far away, they become faint. But from the orbit's point of view, the energy is gone. It has left the system. The orbit must respond. This is why the phrase, "the orbit bleeds energy," works if we let it remain metaphorical. Nothing red flows into the void. No material leaks out. The system radiates part of its orbital energy into space-time, and the old orbit cannot survive unchanged. The separation decreases. The rhythm rises. In a waveform, this becomes visible as a rising pattern. The waves from the early in spiral are lower in frequency. As the black holes move closer, the wave frequency increases. The amplitude also grows as the system radiates more strongly. To a scientist reading the data, the signal is not merely a trace. It is the changing orbit written as time frequency and strength. To a listener hearing a converted signal, it becomes a chirp. The chirp is not sound crossing space from the black holes. It is a translation of the gravitational wave pattern into an audible form. But as a human aid, it is powerful. The rising tone lets us feel the final acceleration. The black holes are orbiting faster, drawing closer, and entering the last stage of their shared motion. The sound is a doorway. The physics is the shrinking orbit. Long before black hole mergers were directly detected, scientists had already seen a quieter sign that gravitational waves were real. One of the most important examples came from a binary pulsar, a pair of neutron stars orbiting each other. A pulsar is a rapidly rotating neutron star that sends beams of radiation across space like a lighthouse. If its pulses reach Earth regularly, they can be timed with extraordinary precision. In a binary system, that timing can reveal changes in the orbit. The famous Hulse-Taylor binary pulsar showed that its orbit was slowly shrinking. The rate of shrinkage matched the prediction from general relativity for energy loss through gravitational waves. No gravitational waves were detected directly from that system at the time, but the orbital decay gave powerful indirect evidence. The orbit was changing exactly as expected if energy was being carried away by space-time ripples. This matters for our black hole story because it shows that the idea of an orbit bleeding energy was not created only after LIGO. The universe had already given hints. A binary pulsar is not the same as a binary black hole, but both belong to the family of compact objects. Neutron stars are incredibly dense stellar remnants. Black holes are more extreme still. When compact bodies orbit, their motion can become a laboratory for gravity. The more massive, compact, and fast-moving the system, the stronger the gravitational wave emission can become. The Hulse-Taylor pulsar was like hearing a clock slowly change its rhythm. The pulses arrived with exquisite regularity, but the orbit itself was losing energy. The timing revealed that the two neutron stars were gradually drawing closer. It was a slow confirmation that space-time was carrying energy away, just as the theory predicted. For black holes, the final version of this process is more intense. The in-spiral is not merely a subtle orbital change detected through timing over years. Near merger, the black holes move so close and so fast that the gravitational waves become strong enough to be detected directly across cosmic distance. The same basic idea, energy lost through space-time ripples, becomes powerful enough to open a new astronomy. This gives Section 4 a deeper historical layer. We do not need to pause for a long history of gravitational wave science, but it helps to know that the shrinking orbit has a heritage. The idea was tested in quieter systems before black hole mergers were heard. The universe first taught us to trust the mechanism through patient timing, then later revealed it in a brief, dramatic chirp. Slow evidence prepared the way for sudden recognition. Now return to the two black holes. Their orbit is changing far more violently near the end than the binary pulsar's slow decay. The pair is compact enough that the gravitational wave emission grows rapidly. The waves carry away energy with increasing efficiency. The final stages become impossible to ignore if one has the right detector. But from within the scene, there is still no ordinary noise. The violence is geometric. This is the quality that makes black hole mergers so difficult and so beautiful to explain. On one hand, they are among the most energetic events known. On the other, if no matter shines nearby, they do not fill space with light. The drama belongs to curvature, motion, and waves. The universe is doing something immense in a language our senses did not evolve to understand. Science gives us the translation. The waveform becomes the sentence. The detector becomes the page. The models become the grammar. When the rising pattern matches the prediction, the invisible orbit becomes legible. This turns the in-spiral into more than a prelude. The in-spiral is where the information accumulates. The frequency rise tells us how fast the orbit is tightening. The amplitude helps reveal distance and mass. The exact shape of the curve depends on the physical properties of the system. The final merger may feel like the climax, but the in-spiral gives scientists much of the story. In a calm visual narration, this is useful. We can imagine each orbit as a line being written into the future signal. The early lines are broad and slow. The later lines grow tighter and darker. The handwriting becomes denser until it reaches the merger. The final page is short, but the script has been forming for ages. This is where the documentary needs to move slowly, because the process is easy to state and hard to absorb. Two black holes orbit. They emit gravitational waves. The waves carry energy away. The orbit shrinks. But this is not just a mechanism. It is the entire path by which a dark, almost invisible pair becomes a detectable cosmic event. Without gravitational waves, the final merger would not be explained in the same way. The waves are not only messages sent after the fact, they are part of the process that brings the black holes together. They drain orbital energy during the in-spiral. They carry away disturbances during the merger and ring down. They allow the system to move from two orbiting horizons to one settled horizon. The messenger is also the mechanism. That dual role is beautiful. It means the same phenomenon that makes the merger happen in the long run also lets us learn about it later. The waves carry energy away from the source, and then after crossing the universe, they carry information to the detector. The black holes write their motion into space-time, and space-time preserves the handwriting. Picture the pair again. The first orbits we imagined were wide and almost restful. Now the separation is smaller. The black holes sweep around the center more quickly. The background stars, if visible, appear more distorted by the changing gravitational field. A scientific visualization might show ripples leaving the system in widening rings, not because the waves are literally colored, but to help the mind follow what is otherwise invisible. The rings move outward, the black holes move inward. This paired motion is the essence of inspiral. Energy goes out, separation goes down. The waves carry the old orbit away from the system. The black holes do not chase the waves, they respond to the loss the waves create. The universe keeps the account in geometry. At first, this may feel almost abstract, but the consequence is concrete. The pair will not remain two forever. If the black holes are close enough, the inspiral accelerates toward an end. There may be a long period where change is slow, followed by a late stage where everything happens quickly. The time scale depends on the masses and separation. For some systems, the final signal that reaches detectors is brief, but the hidden preparation has been immense. This creates one of the central time contrasts of the documentary. A long story can end in a short sound. The black holes may have formed from stars that lived and died before Earth had complex life, depending on their distance and history. They may have orbited across spans too large to picture. Their waves may have traveled through the universe for ages. Yet the strongest part of the signal can pass through a detector in less than a human breath. The universe compresses the ending. The detector later unpacks it. In the late inspiral, the black holes are moving through strong gravity. Newtonian intuition becomes less reliable. The curved space-time description becomes essential. Scientists use general relativity and numerical simulations to model the waveform. The shape of the signal depends on the mass's spins and orbital dynamics of the pair. This is why black hole mergers are tests of gravity. They allow scientists to compare real signals with predictions from general relativity under extreme conditions. The universe creates a situation no laboratory can reproduce: two horizons orbiting at enormous speeds. Space-time itself changing rapidly, gravitational waves carrying energy away. When the observed waveform matches the theory, it strengthens confidence in the theory. If someday a signal deviates in a clear and reliable way, it could point to new physics. For now, the important thing is the pattern. The orbit shrinks, the waves rise, the final merger approaches. There is no need to imagine panic in the system. Black holes have no fear, no intention, no awareness of their fate. The drama belongs to the geometry, not to desire. The motion is enough. Two horizons circle through space-time, creating the waves that make their separation slowly disappear. Each orbit spends distance. That phrase can hold the mechanism gently. The pair spends distance by radiating energy. The old wide orbit is paid out into the universe as gravitational waves. The remaining orbit is smaller, faster, deeper in gravity. The dance continues, but the floor has narrowed. By the end of this section, the two black holes are no longer distant partners in a wide, dark orbit. They are close enough that simple pictures begin to fail. The space between them is strongly curved. The waves are strong. The final cycles approach. What had been a long spiral is becoming a rapid transformation. To understand what follows, we need to change how we see. A telescope may not show us the merger directly. A photograph may not capture two black holes merging in empty space. Yet scientists can visualize the event through warped light simulations, waveforms, and the mathematics of curved space-time. The invisible can be made intelligible, not by pretending it is bright, but by showing the structures it creates. The orbit has tightened. Now we must learn how to picture what no telescope can simply see. In the final approach, the imagination needs a new kind of vision. The old picture of two dark circles can begin the story, but it cannot complete it. Near merger, the black holes are surrounded by a space-time that is moving, bending, and reorganizing too strongly for ordinary images to remain enough. A simple drawing can show two bodies and a spiral path. It cannot show what the geometry is doing. So scientists build pictures from physics. These pictures are often beautiful. Two black spheres orbiting a star field warped around them, colored ripples expanding outward, grids bending like fabric under invisible weight. They can feel almost like scenes from a dream. Yet their purpose is not fantasy. Their purpose is translation. A black hole merger gives us few familiar visual anchors. If no gas surrounds the pair, there may be little or no light from the merger itself. A telescope collects photons, and the central horizons send none from within. The event is happening in gravity. Its strongest messenger is a gravitational wave. To visualize it, scientists must show effects rather than surfaces. One effect is gravitational lensing. Light from stars or galaxies behind the black holes can be bent around them. The background may appear stretched, duplicated, or curved into arcs. As the black holes orbit, the distortion changes. A fixed star field can look alive because the paths of light are being redirected by a moving gravitational field. This gives the darkness a visible edge, not a surface edge, but a boundary revealed by distorted light. The black holes remain dark, yet the sky around them becomes a map of their influence. A star that should appear behind the pair may show up beside them. A point of light may become a crescent. The familiar background becomes folded by gravity. In a visualization, this effect can be slowed down. The viewer can watch the star field twist as the black holes move. The orbital pattern becomes visible through what happens to the light behind it. This does not require the black holes to shine. It requires only that something farther away sends light past them. If gas is present, another visual layer appears. Gas near black holes can heat as it falls inward, forming disks or streams. In some systems, glowing matter can outline the environment dramatically. It can reveal orbital motion turbulence and gravitational disturbance. Around supermassive black holes, or black holes embedded in gas-rich regions, electromagnetic signals may sometimes accompany gravitational events. But for many stellar mass black hole mergers, the cleanest expectation is darkness. That is not disappointing. It is scientifically revealing. The event does not need a visible flare to be real. A black hole merger can be known through space-time rather than through light. The lack of brightness becomes part of the identity of the phenomenon. Scientific visualizations therefore work carefully between truth and imagination. They may color space-time curvature to show strength. They may draw expanding rings to represent gravitational waves. They may use a grid to suggest geometry. None of these features should be mistaken for literal materials in space. The colors and grids are teaching tools chosen so the human eye can follow invisible structures. A good visualization says this is what the physics is doing, shown in a form you can perceive. That is different from pretending a camera was there. The distinction matters because black hole mergers are too easily made into spectacle. A dramatic image can turn them into fiery monsters or magical whirlpools. The more accurate wonder is quieter. The central bodies are dark. The waves are invisible. The space-time curvature has to be inferred, modeled, calculated, and translated. Science extends sight by building disciplined images. A waveform is one of those images. It may not look cinematic at first. It is a line that rises and fades, a trace of changing amplitude and frequency over time. Yet it is one of the most faithful visual forms of the merger. The early part of the line corresponds to in spiral. The rise corresponds to faster orbit and stronger waves. The peak marks the merger. The fading oscillation is ring down. In this line, the event becomes readable. The waveform is not a picture of black holes as the eye might see them. It is a picture of their motion as space-time carried it to us. It translates the final dance into a shape on a graph. Scientists can compare that shape with simulations and extract physical meaning, masses, spins, distance, and the nature of the final black hole. A simulation and a waveform therefore reveal different faces of the same hidden event. The simulation helps the mind imagine motion curvature and horizon behavior. The waveform shows how the event arrives as a signal. One is spatial and visual. The other is temporal and mathematical. Together, they let us approach something no human eye could directly witness. This approach became possible through numerical relativity. Einstein's equations describe gravity as curved space-time, but the final merger of two black holes is so complex that exact simple solutions are not enough. Computers are used to solve the equations in extreme conditions, modeling how the black holes orbit, how their horizons evolve, and what gravitational waves are produced. This is not a replacement for observation. It is a bridge between theory and signal. When a detector records a gravitational wave, researchers compare the observed pattern with predicted waveforms. Those predictions depend on simulations and approximations rooted in general relativity. If the shapes match the invisible event gain's structure, the signal becomes more than a disturbance. It becomes a reconstruction. In a sense, scientists do not simply see the black holes. They infer the event from the marks it leaves on space-time. This may sound less satisfying than a photograph, but in some ways it is deeper. A photograph shows light from a surface or environment. A gravitational wave signal comes from the motion of the system's gravity itself. It reaches us from a region where light may offer little or nothing. It gives access to the dynamics of the merger rather than only to its surroundings. The event becomes visible to thought. One way scientists create these images is through ray tracing. Ray tracing follows the paths that light would take through curved space-time. In ordinary computer graphics, ray tracing can show reflections, shadows, and the way light moves through a scene. Around black holes, the same general idea becomes much stranger. The paths are not straight because gravity changes the geometry through which light travels. A ray of light passing near a black hole may bend sharply. A ray passing closer may loop around before escaping. A ray crossing the horizon does not return at all. When these paths are calculated carefully, they reveal what a distant observer might see if background stars, gas, or a glowing disk were present. The result can look uncanny because the black hole is not producing the light, but rearranging the light from elsewhere. This is why a black hole image often feels like a lens and a shadow at once. The shadow is the region from which light does not escape to the observer. The lensing is the bending of light around that region. Together, they form a visual object that is not really an object in the ordinary sense. It is an image made from absence and distortion. For a binary merger, ray tracing becomes dynamic. The black holes move. Their gravitational fields change. The paths of light shift from moment to moment. A background star field may appear to swirl, split, or tremble as the pair orbits. A distant galaxy behind the system may be warped into changing arcs. The viewer is not seeing the black holes shine. The viewer is seeing the universe behind them being rearranged by their motion. This gives visual storytelling a strong foundation. Instead of showing black holes as glowing monsters, the script can show their effect on the background. Darkness becomes visible by how it bends the scene behind it. Motion becomes visible by how the distortions change. The merger becomes visible by the way separate centers of distortion become one. Another visual method is to show space-time curvature itself. The familiar rubber sheet image is limited, but it can still help at first. A heavy ball placed on a stretched sheet creates a dip. A smaller ball rolls around it. The image suggests that mass curves a surface. But real space-time has 3 dimensions of space plus time, not a 2-dimensional sheet. The black hole does not sit on top of space. It curves space-time in all directions. So, a better narration can use the rubber sheet briefly, then move beyond it. The sheet helps the listener begin. The black hole merger requires more. 2 black holes are not dense moving on a surface. They are strong curvatures moving through a 4-dimensional geometry. A simulation grid can show this symbolically, but the viewer should understand that the grid is not space itself. It is a visual aid for a deeper structure. This careful explanation protects the wonder. It says the real thing is stranger than the picture. That is the opposite of reducing the event. Instead of making the visualization seem less meaningful, it makes the actual merger feel larger. The image is a bridge, and the reality on the other side is even more difficult and beautiful than the bridge can fully show. There is also a difference between visualizing space-time and visualizing the signal. A space-time visualization asks, what might the region around the black holes look like if we could represent curvature horizons and distorted light? A waveform asks, what pattern did the event send to us? These 2 forms should not be mixed carelessly. One is a picture of the source. The other is a picture of the messenger. Together they create a layered way of seeing. First, the mind sees the pair. Then it sees the distortion. Then it sees the waves leaving. Then it sees the waveform arriving. Each layer is a translation, and each translation reveals a different part of the event. For a sleep documentary, this layered seeing can be slow and immersive. The camera of imagination begins far away, looking at a quiet star field. The stars warp as the black holes move. The view shifts to a symbolic grid where the curvature deepens and turns. Then the perspective moves outward, where waves spread into space. Finally, the image becomes a line of data on Earth, a rising and fading trace. The same event passes through 4 visual languages: sky, geometry, wave, data. This prevents the section from becoming only a warning about simulations. It turns simulation into a form of guided perception. The viewer does not need to believe that the colors are literal. They need to understand what the colors mean. They do not need to imagine a real grid in space. They need to feel that space-time itself is structured and changing. The visual honesty is part of the calm. No trick is needed. The universe is already strange enough. Let us imagine a carefully made visualization. 2 black horizons circle dark and smooth. Behind them lies a field of stars. As the black holes move, the stars appear to bend and stream around the horizons. Some light loops in strange paths. The background does not remain fixed because the gravitational field is changing. Around the pair, colored patterns show the strength of curvature or the outward motion of gravitational waves. Nothing in the image is casual. The dark centers represent horizons. The warped background represents lensing. The ripples represent waves. The chosen colors help separate effects. The camera angle helps the viewer follow the orbit. The speed may be slowed so the mind can dwell in a process that near the end would happen very quickly. This is how visual explanation works. It gives the event a human tempo. The full story of the merger contains several timescales. The formation of the pair may take millions or billions of years. The in-spiral may be long. The final orbits of stellar mass black holes can be brief. The wave may then cross the universe for ages before reaching Earth. A documentary must slow and stretch these layers so the listener can feel their relationship. The visualization helps hold them together. It shows the final motion, while the narration reminds us that the final motion is the end of a much longer story. It shows the ripples leaving, while the narration prepares us to follow them across space. It shows the horizons drawing together, while the physics tells us that the merger is not a collision of surfaces, but a reorganization of space-time. A visual image, then, is not the end of explanation. It is the beginning of a more careful seeing. This careful seeing also helps us avoid a common mistake, thinking that if something is invisible, it must be vague. Black hole mergers are invisible to ordinary light, in many cases, but their gravitational wave signals can be precise. The waveform can be measured, the model can be tested, the signal can be compared across detectors. The darkness is not an excuse for guesswork. The unseen can be exact. This is one of the deepest shifts in modern astronomy. Seeing no longer means only receiving light. It can mean detecting a neutrino. It can mean measuring radio waves. It can mean mapping X-rays. It can mean recording gravitational waves. Each messenger requires translation. Each reveals a different layer of the universe. For black hole mergers, gravitational waves are the central messenger. They do not show us a glowing surface. They show us the final motion of space-time around the pair. They let us read what the event did rather than what it illuminated. This is why two dark objects can become one of the most important observational sources in modern physics. The black holes remain visually dark. The event becomes intellectually bright. As the pair nears merger, the limits of visualization become part of its honesty. No diagram can fully capture the curvature. No image can make the event simple. No simulation should be mistaken for a direct recording. But by layering lensing horizons, waves, and waveforms, we can build a picture faithful enough for understanding. That picture will guide us into the next stage. The orbit is now tight. The black holes sweep around each other rapidly. Their horizons distort. The wave signal rises. The distinction between two separate objects begins to lose its stability. The final transformation is close. The viewer has learned how to see the event without expecting ordinary light. Now the final spiral can unfold. The final orbits do not feel like the beginning of a crash. They feel like a pattern reaching the end of its own possibility. The black holes are now close. The orbit that once seemed wide and patient has become fast, tight, and deeply curved. Gravitational waves pour energy away from the system. The rhythm rises. The distance between the horizons continues to shrink. What was once a pair is approaching the moment when separation will no longer describe the geometry well. This is the late in spiral. The word in spiral carries motion and inwardness at once. It is not a fall straight down. It is a curve becoming smaller, a repeated turning that has almost used up its room. The black holes still miss each other with every orbit, but the misses are now extremely narrow. The dance is becoming too tight to remain a dance between two. In a waveform, the late in spiral appears as the rising part of the signal. The frequency climbs as the black holes orbit faster. The amplitude grows as the gravitational waves strengthen. The curve becomes denser, more urgent in shape. though the event itself has no urgency in a human sense. It is simply gravity carrying its consequences to completion. If translated into sound, this part becomes the rise of the chirp. But the real event is geometry. The horizons are not surfaces waiting to strike. They are boundaries in space-time. As the black holes approach, the region around them becomes strongly dynamic. The gravitational fields overlap in ways that simple images can only suggest. The space between them is no longer a calm gap. It is part of the final transformation. Then comes merger. At this stage, language becomes delicate. We can say, the black holes collide because that is the common term. We can say they join because that is the outcome. But the most accurate feeling is that two separate horizons are replaced by one. The system stops being describable as two black holes in orbit and becomes a single black hole in the process of settling. Two boundaries of no return become one boundary. The final moment can be extremely brief for stellar mass black holes. A history prepared over immense time may complete its strongest transition in less than a second. That contrast gives the merger its strange temporal beauty, long formation, slow in spiral, rapid union, and then a fading trace that travels through the universe for ages. The final step is quick. The meaning is vast. Near the very end, even the idea of a stable orbit begins to lose its usefulness. Earlier in the inspiral, the black holes could be described as circling in a way that still resembles orbit. The path shrinks, but the rhythm is clear. In the last moments, the motion enters a more complex regime. The pair is so close that the future is no longer a sequence of many clean circles. It is a plunge into merger guided by the strong curvature of space-time. The word plunge should not be imagined as a fall through ordinary space. It is the loss of a separate orbital identity. The two-body picture gives way to one evolving space-time. The horizons distort approach and are enclosed by a common horizon. The system stops being a binary in any meaningful sense and becomes the birth of one black hole. This is where numerical simulations become essential. The final merger cannot be fully captured by simple analogies. The equations must be solved in the strong field regime where space-time is highly curved and rapidly changing. Computers follow the evolution of the geometry, tracking how the horizons behave and what gravitational waves are emitted. Without this work, the final moments would remain far harder to interpret. The result, however, can be narrated calmly. The orbit tightens beyond the point of return. The last distinction between the two horizons fades. A common horizon forms around what had been a pair. The new black hole is born distorted, carrying the energy of its formation in the shape of its surrounding space-time. It then radiates away that distortion. This gives the ringdown its emotional place. It is not merely the last part of a waveform. It is the universe smoothing the result of the merger. The final black hole does not remain irregular forever. It settles into the simple character allowed by black hole physics, mass spin, and perhaps electric charge, though astrophysical black holes are expected to have negligible net charge. The messy formation leaves behind a remarkably simple object. This is one of the surprising ideas behind black holes. They can have complex histories, but their final external description is simple. A black hole formed from stellar collapse, a black hole grown through accretion, and a black hole formed through merger can all settle into a state described by only a few properties. The past is not written on a visible surface. Much of the complexity is carried away or hidden behind the horizon. For the merger, gravitational waves carry part of that complexity outward. They are the departing record of the event that the final black hole no longer visibly displays. This is why ringdown matters for testing physics. If the final object is truly a black hole, as described by general relativity, the ring-down frequencies and decay should match the expected pattern. The fading signal becomes a test of the remnant's identity. The quiet after the merger is therefore not empty. It is the result of a completed adjustment. The final black hole has become simple because the universe has carried away the disturbance. A newly formed black hole is not instantly in its calmest state. It has been born from a violent change in space-time. Its horizon is temporarily distorted. The surrounding geometry still carries the imprint of the merger. The new object must settle. This settling is called ring-down. The name suggests a bell after it has been struck, and the analogy is useful as long as we remember that no ordinary sound is involved. The final black hole vibrates gravitationally. It radiates away its remaining distortions as gravitational waves. The signal fades in a pattern determined by the properties of the new black hole. Ring down gives the merger a quiet ending. The strongest part of the event has passed. The two original black holes are gone as separate objects. The final black hole approaches a stable form, described mainly by its mass and spin. The waves carry away the last unevenness of the formation. The storm becomes a shape. The shape becomes calm. This is one of the most restful images in the whole subject. A process of enormous power does not end in scattered wreckage. It ends in simplification. Two horizons, two masses, two spins, and a changing orbit become one horizon, one final mass, one final spin. The complexity of the last dance is carried outward by the gravitational waves. The final black hole is slightly less massive than the simple sum of the two original black holes because part of the system's mass energy has been radiated away. In events like GW 150914, this loss was not a minor detail. It was a central part of the gravitational wave signal. Energy left as ripples in space-time, and those ripples traveled across the universe. This is why gravitational waves are not merely reports. They participate in the event's completion. They remove orbital energy during in-spiral. They carry away the intense disturbance of merger. They allow ring-down to fade. They make it possible for the final black hole to settle into a simpler state. Then after doing that work at the source, they continue outward as messengers. The same waves that help the system become calm later tell distant observers how that calm was reached. A waveform preserves the phases, in spiral merger, ring down. A rising rhythm, a peak, a fading oscillation. To the eye, it may look like a compact shape in data. To the physicist, it is the story of strong gravity. To the listener translated carefully, it is a brief chirp from an event older and farther away than the sound suggests. Inside that small shape are the last orbits. This is how a detector on Earth can later reconstruct the event. The signal carries information about the masses of the black holes, their final union, and the settling of the remnant. Scientists compare it with models from general relativity. When the agreement is strong, the invisible merger becomes an observed physical event. The last orbits become evidence. The merger becomes a test. The ring down becomes a confirmation that the final object behaves like a black hole predicted by relativity. For now, remain at the source a little longer. Imagine the scene after the merger. The two separate shadows are gone. One larger black hole remains. If no gas surrounds it, there may be almost nothing visible to mark the change. A telescope searching for light might not see a flare. The region may look as dark as before, perhaps even simpler than before. But the quiet is deceptive. The waves have already left. They move outward in all directions, expanding away from the place where the merger occurred. They carry the final orbits with them as a pattern. The new black hole may settle quickly, but the memory of its birth continues to travel. This gives the merger two different endings. At the source, it ends when the final black hole rings down and becomes stable. For the rest of the universe, the event continues as a wave front crossing space. A civilization far away might receive the signal long after the black holes have merged. Another world elsewhere might lie in a different direction and receive the same ancient event at another place in cosmic geometry. The merger does not send a message with intention. It simply releases a physical trace, and that trace expands. The local darkness closes. The ripple travels on. This is the threshold between Section 6 and Section 7. We have watched two horizons become one. We have seen the new black hole settle. Now the source is quiet, but the gravitational waves remain in motion. They will cross galaxies, empty regions, and deep time. They will weaken, but not immediately vanish. They will carry the shape of the event toward any instrument sensitive enough to recognize them. The collision is over. The ripple is just beginning its long journey. At the source, the event is finished. One black hole remains where two once circled. Its horizon has settled. The last ring down has faded from the local space-time. If the region is clean and dark, little may remain for ordinary light to reveal. The place of the merger has returned to quiet, but the quiet is local. The gravitational waves are still moving outward. They expand through space at the speed of light, carrying the final motion away from the source. They do not carry fragments of the black holes. They do not carry flame or dust or debris. They carry a pattern of stretching and squeezing in space-time, a faint record of how the last orbits unfolded. This is the afterlife of a black hole merger. A ripple in water can outlive the splash that made it. Long after the center calms, the rings continue outward, widening and weakening. A gravitational wave is not made of water, and there is no cosmic lake beneath it, but the analogy helps the mind begin. Something happened. A disturbance spread. The source became quiet before the signal finished traveling. The wave crosses regions no human eye could meaningfully picture. It moves beyond the immediate neighborhood of the black hole. It passes through any surrounding stars or gas with almost no resistance. It enters the wider galaxy. It crosses spaces where matter is thin, where the nearest bright object may be far away, where darkness is not a wall but an immense distance. Matter barely stops it. This is one of the reasons gravitational waves are such powerful messengers. Light can be blocked, scattered, absorbed, or trapped. Dust can hide stars. Gas can reshape radiation. Event horizons can prevent light from escaping at all. Gravitational waves from a merger pass through ordinary matter with extraordinary ease. They can travel from the strongest gravitational regions to distant detectors, keeping the imprint of the motion that created them. They carry information without needing brightness. The wave structure depends on the source. The in-spiral shapes the rising frequency. The merger shapes the peak. The ring-down shapes the fading oscillation. The masses of the black holes, their spins, their distance, and the final black hole all leave traces in the signal. A gravitational wave is not only evidence that something happened, it is evidence of how the happening moved. As it travels, the wave becomes fainter. It spreads over a larger and larger sphere. The energy is distributed across cosmic distance. Near the source, the waves may carry immense power. Far away, their effect becomes extremely subtle. By the time such a wave reaches Earth, the stretching and squeezing it causes is smaller than anything human senses can feel. This contrast gives the journey its quiet force. The origin is extreme. The arrival is delicate. The wave may cross millions or billions of years of distance. While it travels, stars form and die. Galaxies slowly change. Planets cool. Life may appear somewhere. On Earth, entire histories can unfold while the wave is still on its way. The merger itself is ancient by the time it reaches us, but the arrival happens in the present. Astronomy always deals with delayed messages. Light from a distant galaxy shows the galaxy as it was when the light began its journey. A gravitational wave does something similar, but with a different messenger. It carries not an image, but a motion. It lets the past touch the present through a tiny change in distance. The wave is old when it arrives. The recognition is new. The wave also carries the expansion of the universe in its journey. As it travels across cosmic distance, space itself may stretch. The wavelengths of light from distant galaxies are stretched by cosmic expansion, and gravitational waves can also be stretched in a similar way. The signal that arrives at Earth may therefore be affected not only by the merger, but by the vast distance between source and detector. This adds another layer to the idea of the ripple as a messenger. It does not travel through a static hallway. It crosses an evolving universe. Galaxies move apart on large scales. Space expands. The wave continues carrying the original event while also bearing the marks of the cosmos it has crossed. For the listener, the simplest feeling is this: the signal arrives aged by distance. It began with a fast, violent motion near two black holes. It crossed a universe wide enough to stretch even the messengers that move at light speed. By the time it reaches Earth, it is faint, ancient, and still meaningful. The wave has not preserved the event by freezing it unchanged like an object in a box. It has preserved it as a traveling pattern through a changing cosmos. This makes the detector's work even more remarkable. It must read the source and the journey together. The waveform carries the masses and motion of the black holes, but distance affects how strong the signal appears. Cosmological expansion can affect how the masses are inferred through redshift. Scientists must interpret the arrival carefully because the universe itself has shaped the message on its way. The ripple is therefore not only a bridge across space, it is a bridge across cosmic history. Think of how much can happen while a gravitational wave travels. Stars that did not exist when the wave left its source may form before it arrives. Worlds may cool, atmospheres may change, life may arise or vanish. Civilizations may build, sleep, fail, begin again. The wave continues without awareness, moving through all of it. This gives the journey a dreamlike calm. The wave does not hurry, even though it moves at the fastest speed information can travel. The universe is simply too large for speed to feel simple. What is fast locally can still take ages cosmically. The wave is swift and ancient at the same time. By the time it reaches Earth, the black holes that made it are no longer in the state the signal describes. They have long since become one. The source has aged. The final black hole may have moved through its galaxy. Other events may have happened nearby. Yet the wave carries the source as it was at the moment of merger. It is a past tense moving through the present. This is one of the quiet emotional strengths of astronomy. The sky is never only now. Every distant signal is a kind of memory. Light remembers stars. Radio waves remember gas. Gravitational waves remember motion in space-time. To observe the universe is to receive delayed truths, each arriving from a different depth of time. The black hole merger becomes part of that larger pattern. It is not visible like a star, but it too has a past that arrives. The ripple is the way that past reaches us. This layering of time is one of the most peaceful parts of the story. Somewhere far away long ago, two black holes finished their final orbit. The wave left. It traveled without attention, without audience, without needing to be understood. It passed through the universe as the universe continued to evolve. For most of its journey, there was no witness. Then much later, it reached a small planet around an ordinary star. There is humility in this. The wave was not aimed at Earth. The black holes did not merge for us. The signal was not sent as a message with intention. It expanded in all directions because that is what space-time does when disturbed in that way. Earth happened to lie along one path of the expanding wavefront. We became accidental listeners. Before the wave reaches Earth, imagine its path through the Milky Way. It enters the galaxy quietly if its route brings it there. It passes through the halo, through regions of sparse gas and dark matter, through the broad structure of stars. It crosses the galactic disk without disturbing it in any obvious way. It passes near stars, planets, dust, magnetic fields, and clouds. Almost nothing notices. Then it enters the solar system. It moves past the outer planets, through the vast dark between their orbits, past the sun's influence, past Earth's path. It does not arrive as a beam or a flash. It is not narrowed like a spotlight. It is part of an expanding ripple that simply reaches this region of space. When it passes through Earth, mountains do not tremble. The atmosphere does not glow. Oceans do not rise. The human body feels no touch. The wave is too faint after its long journey to affect ordinary matter in any noticeable way. It slips through stone, water, metal, wood, and sleeping cities. Still for a moment, distances change. One direction stretches very slightly. Another direction squeezes very slightly. Then the pattern reverses. This is not movement through air or a shaking of the ground in the familiar sense. It is a change in the geometry between points. The effect is almost impossibly small. That smallness is not a failure of the wave. It is a consequence of distance. The signal has crossed an enormous universe. Its faintness is part of its story. To detect it, an instrument must do something extraordinary, separate this tiny space-time pattern from the endless noise of Earth. This is where the ripple becomes a challenge. The universe has delivered the message, but Earth is not a quiet receiver by default. The ground moves. Winds blow. Waves strike coastlines. Machines operate. Trucks pass. Thermal motion stirs materials. Even the instruments themselves have noise. To hear a gravitational wave, scientists had to build a system that could recognize a cosmic whisper inside a noisy planet. The ripple outlives the collision, but detection requires preparation. The wave carries the memory of the final orbit. That memory can be read only if the listener is precise enough. Without the right instrument, the wave passes through and is gone unnoticed, like countless other ripples that may have crossed Earth before humanity knew how to listen. This makes the journey of the wave both vast and fragile. Vast, because it crosses cosmic distances. Fragile, because its recognition depends on a tiny measurement made at the right moment. The wave itself does not stop at Earth. It continues onward, leaving our planet behind, still spreading, still weakening, still carrying the old event into deeper space. But for a brief moment, while it is here, it offers a chance. If a detector is ready, the motion of two black holes can be captured. This is where the story turns from cosmic scale to human precision. The source has finished. The wave has traveled. The planet has been crossed. Now the question becomes almost unbelievable in its delicacy. How can an instrument measure a change in distance so small that ordinary language barely has room for it? How did Earth learn to hear the dark? The wave passes through Earth in near silence. No one standing outside would notice. No birds would lift from trees. No glass would tremble on a table. The signal would not ring through the air or disturb the ground like an earthquake. A gravitational wave from a distant black hole merger arrives with a gentleness that seems almost impossible when we remember where it came from. Inside the right instrument, however, the silence becomes measurable. The instrument is not a telescope in the usual sense. It does not gather light from the merger. It does not form an image of two black holes. It waits for distance itself to change. This is the idea behind LIGO, the Laser Interferometer Gravitational Wave Observatory. Picture two long arms extending at right angles across the landscape. A laser beam is split and sent down both arms. Mirrors reflect the light back. The returning beams meet again. Under ordinary conditions, their pattern is controlled with extraordinary precision. If a gravitational wave passes through, it changes the length of one arm relative to the other by an unimaginably tiny amount. That change affects how the laser beams recombine. The light becomes a ruler for space-time. This is a simple idea carried to an extreme of difficulty. The arms are kilometers long. The mirrors must be isolated from ordinary vibrations. The laser must be stable. The vacuum system must allow light to travel cleanly. The data must be filtered, checked, compared, and tested against countless possible sources of noise. Earth is restless. Wind presses on buildings. Seismic tremors move through the ground. Ocean waves create distant vibrations. Human machines add their own disturbances. Even microscopic thermal motions and quantum effects can matter at the level of precision required. To hear a black hole merger, scientists had to understand not only the universe, but the noise of the planet beneath their feet. This gives LIGO its quiet drama. It is a machine built to notice what should be almost unnoticeable. It listens by comparison, by patience, by control of disturbance. It makes no journey to the black holes. It waits on Earth until space-time itself passes through. The use of more than one detector is essential. A disturbance near one observatory could come from local noise. But if a similar signal appears in detectors separated by thousands of kilometers with the correct timing and shape, the interpretation becomes stronger. The two main LIGO detectors, one in Hanford, Washington, and one in Livingston, Louisiana, act together as a way of distinguishing cosmic signal from local accident. The universe is heard by agreement. That agreement is not only between two detectors, it is also between instrument and theory, between data and prediction, between the tiny motion recorded on Earth and the enormous motion modeled in curved space-time. A single instrument can be fooled. A single strange pattern can come from noise. But when the signal appears in multiple detectors with the correct time delay, and when its shape matches a predicted black hole merger waveform, the interpretation becomes powerful. This is how the invisible becomes trustworthy, not through one dramatic moment alone, but through layers of checking. Scientists ask whether the signal could come from the instrument. They ask whether it could come from the environment. They compare the data streams. They match the waveform against models. They estimate the chance of a false alarm. The cosmic story emerges only after the earthly doubts are taken seriously. This is important for the tone of the documentary. The discovery was astonishing, but it was not magical. It did not ask humanity to believe in darkness blindly. It asked scientists to measure, compare, test, and question. The result became beautiful because it survived that process. The black holes were not visible, but the evidence was structured. A gravitational wave detector is therefore an instrument of patience as much as precision. For years it may wait through silence and noise. It may record countless disturbances that are not cosmic signals. It may be improved, adjusted, upgraded, and checked. The desired event cannot be scheduled. No one can tell two black holes when to merge. The instrument must simply be ready when a wave crosses Earth. This waiting gives the human side of the story a quiet dignity. While the black holes completed their ancient motion, people on Earth built long vacuum tubes across flat landscapes. They suspended mirrors so still that ordinary vibration became an enemy. They refined lasers. They wrote code. They studied noise. They prepared models of signals that might someday arrive from events no telescope could see. They were building a way for spacetime to be noticed. When GW 150914 appeared, the signal was brief, but the preparation behind it was not. The moment depended on decades of work on theoretical predictions, engineering challenges, mathematical modeling, and an international scientific community. The chirp lasted a fraction of a second. The listening took generations. This contrast mirrors the cosmic event itself: a long preparation, a brief arrival, a lasting change in understanding. After the first detection, the meaning of the universe shifted slightly. Black holes had already been strongly supported by many lines of evidence, but now their mergers had been directly observed through gravitational waves. General relativity had passed another extreme test. A new observational field had opened. The sky had gained a new sense, not vision in the ordinary way, not hearing in the ordinary way. Something quieter, a sensitivity to the stretching of distance itself. This is why the final image of Earth matters. Our planet is noisy, bright, restless, full of weather and life. Yet within that restlessness, humans created small zones of disciplined quiet. Long arms mirrored ends, laser light vacuum computation comparison. A cosmic ripple passed through everything, and in those carefully prepared places, it became legible. The detector did not overpower the universe. It became delicate enough to receive it. That may be the most fitting ending for a sleep documentary about black holes. Not domination, not conquest, not humanity standing above the cosmos. Only listening. A small planet learning to notice emotion from far away. Emotion born when two regions of darkness became one. The achievement feels almost humble. To hear the dark earth had to become quiet. On September 14, 2015, a signal arrived. It was brief. It was not visually dramatic in the raw human sense. But in the data, it had the form. Scientists had been waiting for a rising gravitational wave pattern, consistent with two black holes spiraling inward, merging, and ringing down into a single final black hole. The event became known as GW 150914. For the first time, gravitational waves were directly detected. For the first time, humanity observed a binary black hole merger. The scale contrast is almost dreamlike. At the source, two black holes, many times the mass of the sun, had merged. Energy had radiated outward as gravitational waves. The waves crossed cosmic distance and reached Earth as a change in length far smaller than an atomic nucleus. A vast event became a tiny shift in laser light. Then the data became a story. The waveform revealed the final orbits. The rising frequency showed the in-spiral. The peak marked the merger. The fading pattern showed ring-down. By comparing the signal with predictions from general relativity, scientists could infer the masses of the original black holes and the final black hole left behind. The invisible dance had become readable. This was not merely the confirmation of a theory, though it was that too. It was the opening of a new way to observe the universe. Astronomy had long expanded by adding new kinds of light radio, infrared, ultraviolet X-rays, gamma rays. Each revealed objects and processes hidden from ordinary vision. Gravitational waves opened a different channel altogether. They are not part of the electromagnetic spectrum. They are space-time in motion. With them, black hole mergers could become observable, even when no light was seen. The dark universe began to offer signals of its own. The sky was no longer only what shines, reflects, or absorbs. It was also what moves strongly enough to ripple space-time. After GW 150914, more detections followed. LIGO was joined by Virgo in Europe and later by Kagra in Japan as part of a growing global network. Additional detectors help locate signals more precisely and increase confidence in events. As observations accumulate, black hole mergers become a population rather than a single astonishment. Each signal adds another piece. Some black holes are heavier than expected. Some pairs raise questions about their formation. Some signals are clearer than others. Some mergers may point toward isolated binary evolution, while others may suggest dense environments where black holes meet through gravitational encounters. The catalog becomes a map of dark histories. This returns us to the earlier sections. The waveform on Earth is connected to the lives of massive stars. It is connected to collapse pairing and spiral merger, ringdown, and cosmic travel. The signal may last only a moment in the detector, but it contains the final movement of a story that began long before Earth received it. A chirp is small, its history is not. When scientists convert the gravitational wave signal into sound, the result can be surprisingly modest, a short upward sweep. The translation helps human beings feel the pattern, but the sound itself is not what crossed space. What crossed space was a ripple in geometry. The audio is a human bridge, a way to let the ear experience a shape, first measured by lasers. That bridge is valuable. It lets us hear the rising orbit, the final tightening, the sudden merger, the fade into ringdown. It turns data into intuition without replacing the physics. In that small chirp, the mind can hold something otherwise too remote to feel. This is what it means for Earth to hear the dark. Not hearing in the ordinary sense, not sound through air. A deeper kind of listening built from mirrors, lasers, mathematics, and decades of persistence. Earth learned to hear by becoming precise enough for space-time to leave a trace. The achievement was human, but the event was cosmic. Scientists did not create the wave. They did not choose when the black holes merged. They could only prepare instruments, refine methods, reduce noise, and wait. Somewhere far away, the universe performed the experiment. The detector received the result. That relationship is humbling. A planet builds a machine. The cosmos supplies the signal. The new astronomy is still young. With each observing run, detectors improve. More signals are found. Models are tested more carefully. Populations are compared. Black holes become not only mysterious endpoints of stellar death, but tools for studying gravity, stellar evolution, dense clusters, and the history of the universe. The dark begins to have statistics. It begins to have patterns. One day, gravitational wave astronomy may reveal many more kinds of events with greater clarity mergers involving neutron stars, black holes of different masses, perhaps signals from supermassive black hole binaries through future space-based detectors, perhaps backgrounds made from many unresolved sources. The field is an opening, not a conclusion. For this documentary, though, the central image remains simple. Two shadows in deep space. A slow orbit. Energy leaving as gravitational waves. A final spiral. One black hole. A ripple crossing the cosmos. Earth much later quiet enough to notice. At the beginning, the darkness seemed like a limit. By the end, it has become a different kind of sky. It contains motions that do not shine, events that do not make ordinary sound, and signals that arrive as changes in distance. The universe is not restricted to the senses we were born with. Human beings learn to extend those senses. A telescope extends the eye. A radio dish extends hearing only metaphorically by receiving waves the ear cannot hear. A gravitational wave detector extends something even deeper, our ability to notice geometry itself changing. That is why the story does not end with the first detection. It ends with a changed relationship to the cosmos. We now know that black holes can merge in darkness and still become observable. We know that space-time can carry news across vast distances. We know that a tiny motion inside a detector can contain the memory of an event far beyond ordinary sight. The dark can speak if the listener is patient enough, and perhaps the quietest wonder is this: the wave continues after passing Earth. It does not stop because we detected it. It moves on, leaving our planet behind, carrying the old merger farther into space. For one brief moment, our instruments shared its path. In that moment, two black holes that had become one long ago became part of human knowledge. A cosmic event entered a line of data. A line of data became a story. And the story taught us that the universe is still moving in ways we are only beginning to hear. By the end of this journey, the collision no longer feels like a single violent instant. It feels like a long transformation. Stars becoming remnants, remnants becoming a pair losing energy through space-time, and two horizons finally settling into one. The black holes themselves may never have shone. Their merger may have left no bright flare for an ordinary telescope. Yet their motion was not lost. It bent the geometry around them, sent gravitational waves outward, and carried the final rhythm of their orbit across cosmic distance. Somewhere on Earth, much later, laser light moved through long, quiet arms. Mirrors waited. Noise was filtered away. A signal passed through the planet so faintly that almost nothing noticed it, except the instruments built for exactly that kind of silence. Inside that tiny trace was a vast event. Perhaps that is the calm wonder of black hole mergers. They remind us that the universe is not limited to what glows. Some of its deepest changes travel as subtler messages, a distortion, a ripple, a pattern in time, a momentary stretching of distance. So, when we imagine the dark between the stars, we do not have to imagine emptiness. We can imagine motion beyond sight. We can imagine invisible pairs circling through deep time waves crossing the universe, and a small planet learning slowly and carefully how to listen. There is something deeply calming in that thought. The universe does not reveal itself all at once. It does not speak in only one language. For most of human history, the sky meant points of light. The moon, the sun, the slow wandering of planets, the glow of the Milky Way. Then instruments widened the sky. Radio waves revealed cold gas and distant galaxies. X-rays revealed violent regions near compact objects. Infrared light pierced dust. Each new messenger changed what the word universe could mean. Gravitational waves changed it again. They showed that space itself can carry a story. They showed that an event hidden from ordinary vision can still become part of knowledge. They showed that the dark is not only a place where light is missing, but a place where motion, curvature, and memory can travel. This does not make the universe less mysterious. It makes the mystery more precise. Now, when we imagine two black holes far away, we do not need to picture only a void. We can picture a slow orbit written in gravity, a shrinking spiral, a final horizon forming, and a faint ripple leaving the source behind. We can picture that ripple crossing distances no human body could survive, passing through galaxies and darkness until it brushes Earth for a moment and continues onward. Most of the time, we will never notice such things directly, but science has taught us that direct human sense is only the beginning. The eye can be extended, the ear can be translated, distance can be measured with lasers, space-time can become data, data can become understanding, understanding can become a quieter kind of awe. The black hole merger remains dark, but it is no longer unreachable. The sky is larger than light, and somewhere in that larger sky, the dark is still speaking.